right here, so I'm not in the way.
Yeah, you're fine. Okay, so I want to talk about law of the conservation of momentum, which comes from Newton's third law. That's why we're talking about it when we're talking about Newton's laws of motion. Conservation of momentum is a direct result of Newton's third law. And I think I tried to show you this when we were talking about Newton's third law. During our demonstration, we had there was a student from the class that was on the rollerblades, and they had a ball and they were throwing the ball. And I've drawn it's a similar picture, but this stick figure is on a skateboard. But the idea is the same, that the momentum of the skateboarder and the ball before he threw the ball is exactly the same of the momentum of the skateboarder and the ball after the ball was thrown. Now, I'm going to show this to you a couple different ways, but basically what I'm saying when I'm talking about momentum, if you remember what the momentum equation is, momentum is equal to, it's a fancy P, so I'm going to draw it like that, is equal to the mass times the velocity, right? So the mass times the velocity is the momentum. But before the ball was thrown, the skateboarder was not moving. Would there be any momentum then? No, there can't be any momentum if there is not any velocity, because anything times 0 is 0. So the momentum of the skateboarder before is 0. So what must the momentum of the skateboarder be after? According to the law of conservation of momentum, it says that the momentum should be? It's 0. You're second guessing yourselves, because now wait a minute, Mr. A, there was velocity. Yeah, the ball was thrown, the ball was moving. I saw it with my own 2 eyes. There was a velocity associated with the ball, and there was a velocity associated with the skateboarder. But mathematically speaking, if we're going to model this mathematically, and we assign a positive velocity to the ball going that direction, what velocity must we assign to the ball, to the skateboarder going this direction? It's got to be a negative. So how can we get to 0 if we have 2 non-zero values? If one of them is negative and you add them together and you get 0. Okay? So that's how that works out. Momentum before equals momentum after. They both have to equal 0. We understand that if there's no velocity, then there's going to be no momentum. But now afterwards, I think I showed you the math that was involved in this. If momentum before had to equal momentum after, then this means that the momentum, I hope I can do this, the momentum before, so this is before, this is after, the momentum before was equal to the momentum of the skateboarder plus the momentum of the ball, right? And both of those were 0, okay? So afterwards, we have the momentum of the skateboarder. So the momentum of the skateboarder plus the momentum of the ball. And what I'm saying is that if the momentum of the skateboarder is, the momentum of the ball is positive, then this momentum of the skateboarder must be negative. Okay? So that when you add them together, you get 0, right? That's what I'm saying basically with symbols. Now, we talked about Newton's third law, that the force on the ball must be equal to the force on the skateboarder. So we had force of, what was it, Tim? Force of Tim on the ball had to be equal to the force of the ball on Tim. And if we're going to break down what the force of Tim on the ball was, that would be the mass of Tim times Tim's acceleration. So this is the mass of Tim times the acceleration of Tim on the ball. This has to be equal to the mass of the ball times the acceleration of the ball. Okay? And we understood this when we had this discussion. How could these both be equal? That's because Tim's mass was much larger than the ball's mass, and Tim's acceleration was much smaller than the ball's acceleration. Okay, so, and then I think I told you that Newton didn't actually write his second law this way. He actually wrote what acceleration was. He actually wrote what acceleration was in terms of the formula for acceleration. So he had mass, but he also had acceleration in terms of the change in velocity over time. So the acceleration is the change in velocity over the change in time. Likewise over here, it was the mass of the ball times the change in velocity of the ball over the change in time. So over here on this side, it's the change in velocity of Tim over the change in time. Over here, it's the change in velocity of the ball over time. Now, you guys know from your algebra, if you have something on this side and you have something on this side, then you can cancel them out. I can't cancel out Tim's mass with the ball's mass because they're different. I can't cancel out Tim's change in velocity with the ball's change in velocity because they're different. But that occurred over the same amount of time. So I can cancel out delta t on this side, and I can cancel out delta t on this side. Now we see where we come up with the law of the conservation of momentum, because momentum is mass times velocity. So the momentum of Tim has to equal the momentum of the ball. So all this is just a bunch of symbols to help you understand the connection between Newton's third law, for every action there's an equal and opposite reaction. Those two forces are the same, expressed through different objects. Using some mathematics, we can get down to say that the momentum has to be equal. So the momentum of the ball has to equal the momentum of Tim, right? And we know that they're both zero because if we take and we subtract the momentum of the ball from both sides, then we get 0. Oops. Yeah, pretty cool, huh? Can I have a round of applause for that?